there, everyone. We're going to go ahead and let folks start coming into the Zoom room. We are so excited to have you for our fantastic chemistry webinar today. We're going to do some really good learning with our excellent presenters. While folks are still filtering into the room and getting comfortable, I'd love to hear from you. Go and navigate down to the chat box at the bottom of the Zoom window there. And let me know if you've joined us for a webinar before or if this is your first time. We love to see who's new, who's been with us before, and kind of just get the conversation going. I'll say as you go ahead and start putting your chats into the chat box, just make sure that your settings are set to everyone can see your chat. That just makes it so that if you're asking questions throughout the webinar, everyone knows what you're talking about. It's a great way to kind of meet other scientists and kind of find out, what other people are wondering, all that good stuff. All right. Yep. Chris, good to see you. Welcome back. And it looks like it's Adam's second webinar. Wonderful. You went to electrochemistry last year. I remember that one.
Yeah. Awesome.
Perfect. Awesome. We have a few returning.
Yay. Ooh, first
Awesome.
time.
Yes. Katrina,
Yay.
welcome. We are so excited to have you.
Oh, quite a few
Hager's,
first timers. Nice.
Yeah.
Hagerstown, Maryland. It's only 30 minutes from my house
Oh, cool.
in Maryland.
Hey, maybe you guys know each other.
I'm trying to remember.
All right. Well, it is 3 o'clock our time here. So to make the most of the time we have together today, I'm going to hop into some housekeeping. Everyone, please feel free to continue using the chat box there. We're going to be watching it to answer your questions. Some important notes to share before we get started. We will be giving you a recording of this webinar. It'll be featured both on our website and on our YouTube channel. You will receive an email with a link to the recording, so keep an eye out on your inbox for that. It usually takes us about 3 to 5 business days to get that video uploaded. That just kind of gives my team time to get it all edited, situated, put up for you. So it takes about that timeline. And as I said, if you have any questions during today's session, please use that chat box that we are talking about right now. We are going to keep an eye on that. I'm going to drop a few links for you in there, so that's going to be a huge tool for us today. And if we happen to not answer your question, please do feel free to reach out to us. You can email us at chemistry@vernier.com. And probably these two folks are going to be right there ready to answer your question. So with that, I will pass you off to today's presenters. Thank you so much for joining us.
Yes, thanks, Dylan. Yep, like she said, we are the two chemists. So I am Melissa. I'm one of the chemists at the company. It's a pretty small company. There's about 100 of us, from everyone that designs the software to develops the products to put stuff in boxes. So there's only two chemists, me and Noose, and we do stuff like this. We do teacher trainings, webinars, we write curriculum, we develop the products. I'm going to be leading the webinar today, and I'm going to let my great support, Noose, introduce himself.
Hi, folks. My name is Noose Hissam. I taught chemistry in Maryland for 34 years and AP chemistry for 25 years. And I'm a chemistry specialist here at Vernier. And this is one of my most favorite things, short of being in the room with you and being able to share something exciting like Melissa has come up with a great idea that I'm hoping will be you guys will get a kick out of. But that's my favorite thing to do, is to share how you can use this technology in your classroom. So let's have at it, Melissa.
Yeah, let's get excited.
I'm going to be answering questions, by the way. So drop them into the chat and I'll try to answer them as best as I can. And if I don't know the answer, I'll bother Melissa.
Yeah, definitely ask questions anytime. This is not meant to be a lecture at all. So Noose is very comfortable interrupting me. So definitely throw your questions in chat as we go. So first off, the Chatelier's principle. Why did we pick this topic? It was the most requested chemistry webinar topic from last year. Of all the webinars we did last year, Dylan always throws out this survey at the end, so stick around for her survey. We do read them. We do listen to your requests. This is the proof. So many people requested a webinar on Le Chatelier's principle. And I can totally understand why. When I taught back in college, it was something students really struggled with. Not only is it a really kind of abstract topic, but it has a lot of math. It has a lot of complex levels to it. So not only at the AP level, but also at the college level. So I understand why students struggle with it, and we as teachers struggle with it too. So the best way to address these struggles is to just come up with more and more hands-on experiments. And I have a really fun one for you today. This is not one that is written up in Vernier land. It's not in any of our books. It is using bromothymol blue acid-base indicator. So it's less expensive than the typical like iron thiocyanate experiments that are written up, and it's more environmentally friendly. So we're really hitting that ACS prerequisite of using green chemistry in chemistry curriculum. But not only that, it's using purely graphical data. So we're not going to do an ICE table today. We're not doing a lot of plugging and chugging. We're going to try and do everything graphical. So if you're really trying to kind of mold your students' graphical skills, this is a really good lesson for that. We'll talk a little bit about some further extensions and some further resources as we go. But the bulk of it is really going to be looking at that one experiment with bromothymol blue. So I'm going to be demonstrating the experiment with our Go-Direct SpectroVis Plus visible spectrophotometer. So you can use any visible spectrophotometer for this experiment. We've had several versions of SpectroVis Plus out there. You can use any of them. We also have other visible spectrometers. We have UV-Vis spectrometers you can use it for. You can even use the colorimeter with this. It's not quite as illustrative, but if you have one spectrometer in a classroom set of colorimeters, highly recommend. You could even, if you don't even have one spectrometer, there is a amazing Google folder that you all have access to by coming here that I'm sure Dylan's going to put the link in just because I said that. And that Google folder has lots of data, and it has all the instructions. It's going to have worksheets in there. So all the instructions are in there. The instructions are for the spectrometer, but it has actual data for the spectrometer. So you could mix that with colorimeter data, and your students would get the same illustrative concepts. So I'm going to be using the SpectroVis Plus and with our free spectral analysis software, but you could also use it with LabQuest. And then we need a pH probe. Again, Vernier has lots of pH probes over the years. We've had cabled pH probes, we have wireless pH probes, we have flat pH probes, we have rounded pH probes. Any pH probe will do. You can use it with, I'm going to be using it with graphical analysis. You could also use it with LabQuest. There is a graphical analysis is free. There is a buy-up option called Graphical Analysis Pro. There's a free code right here. Try it out. Nothing I'm going to be doing today requires Graphical Analysis Pro, but if you think you might be interested, definitely take a look with that free code. All right, so into Le Chatelier's principle. So just a refresher, Le Chatelier's principle states that a system at equilibrium will respond to a change by shifting its position to counteract that change. It's often illustrated with a teeter-totter. Bromothymol blue, I already said I'm using today as the reaction model we're using. And the reason I really like bromothymol blue is because, and here is its reaction. The reason I really like bromothymol blue is because in the acidic form, it is yellow. In its basic form, it is blue. So your eye sees it as blue. In the acidic form, your eye sees it as yellow. Anywhere in between, your eye sees it as green. So it's super visible for your students. It's super illustrative. It's super engaging for your students. It's not just pink and clear, red and clear, red and some other hue of red. So even if you don't have any equipment whatsoever, you could still have your students play around with bromothymol blue and some acids and bases, and they would get a good concept around Le Chatelier's principle as kind of a qualitative concept. But we do have equipment today, and we want to make it quantitative. So let's get going. All right, so this is the structure here, and as I said, in its acidic form, and it's on the reactant side of the equation, it's yellow. On the product side, it's blue. So we're going to take absorbance spectra. On the acidic side, it has this nice peak here at 430. And as you increase the pH, that peak will go away. And you will get a peak that appears from the basic species coming in at 620. So we're going to be making several different samples at several different pHs and measuring the spectra of all these different samples and collecting the pH of all these different samples, taking all that data together and calculating the equilibrium constant of this reaction based on all that data. Well, how are we going to do that, Melissa? Let's take a step back and look at where all that's going to come from. All right, back to basics. Here we go. Here's our reaction equation. Let's write our equilibrium constant. Products over reactants. Okay, here's our equilibrium expression. Products over reactants. Concentration of our products over our reactants. Then we take minus the log. Then we take our pKa, pH minus the log. Now I have my pKa, my Ka expression. I want to linearize this so I can get it from a graph. Needs to look like y equals mx plus b. So I rearrange this equation. It's going to look like this. This is the Henderson-Hasselbalch equation. May look familiar to many of you. Well, what does this mean? This means that if I have a graph of pH plotted against the log of the concentration of the basic form of my bromothymol blue over the acidic form of my bromothymol blue, the y-intercept will give me the pKa of that reaction. Okay, I'm with you. I got a pH probe out. I know where I'm getting pH data from, right? Because I got a pH probe. But where am I going to get this? This is the log of, what is this? What's this? Okay, this is the concentration of the basic form of your bromothymol blue over the concentration of your acidic form of your bromothymol blue. Remember, we have our spectrometers out. We're going to be measuring the absorbance of our basic form at 620 and our acidic form at 430, somewhere in there. And we know from Beer's law that our absorbance is proportional to concentration. So we can get all this information from our absorbance spectra. So we're going to plot that versus our pH readings we get from our pH probe. And then once we plot that, we'll put all that in graphical analysis and get our pKa directly from a linear fit. So that's where we're going. Everyone with me? You excited for this ride? All right, let's start taking some data. All right, as good chemists, before we start taking any data, we have to prepare solutions. So again, in that handy dandy Google folder, I have a worksheet. The first tab is the solutions. Pretty basic stuff. A bromothymol blue stock solution tells you how to make it. Some hydrochloric acid, some sodium hydroxide, and some monoprotic and diprotic phosphate solutions. These do not have to be titrated. They are just 0.1 molar. Easy peasy. You're basically making poor man's buffers here, okay? The instructions do call for volumetric flasks, but I made them in beakers and graduated cylinders. So just a warning out there. This is a camera here live showing you my data. I have already prepared these solutions right here, like I said, in beakers. And I have poured about 1 to 2 milliliters of each of these solutions into a cuvette. So I have done nothing else other than make those solutions and put them into a piece of them into a cuvette. The rest of them is in the beaker because I need to measure the pH and then I need to measure the absorbance spectrum. So that's all that I have done here. Just because we don't have a lot of time today, so I can't make the solutions here for you. But everything else is just set up as if we just started class. All right. So I have connected my spectrometer via USB to my computer, and I'm opening spectral analysis. Spectral analysis, like I said, is free. It is how you collect data from Vernier spectrometers. You can also collect data through a LabQuest, but you need spectral analysis. So it automatically identifies my SpectroVis Plus. Great. We want to take full spectrum data. That's the only way to get both peaks. So we're going to say absorbance versus wavelength. And we're going to let it sit here and warm up. And I'm going to make it a little bit smaller so everyone can see all my screens. Okay, so while that's warming up, some of you Vernier power users out there might be saying, Melissa, you're going to be taking data with a pH probe. I know you cannot use spectral analysis and graphical analysis on the same computer at the same time. It just won't work. You are correct. I could not open graphical analysis right now if I wanted to. That will cause things to crash, and nobody wants that to happen. I could get out my phone and connect it to my pH probe and take pH data on my phone. I could get out my LabQuest. But then I have a second device, and the main reason I'm doing this is to show it to you all. And I should probably be doing that on this computer because that's how you all are seeing what I'm doing. But the other reason I want to use everything on one computer is to show off something really kind of cool that Vernier has been doing. And that is making graphical analysis available as a web app. So you just go, I'm here in Google Chrome. I'm opening up a new tab in my web browser. And all I do is start typing in graphicalanalysis.app. Do it right now. I know you're sitting at a computer, probably, most likely. Open up a new browser, say graphicalanalysis.app, and you will get this exact same screen. Totally free. You don't have to pay for it. If you have a sensor, try it out. Connect to it. I'm going to pull it out so everyone can see what I'm doing. Make it a little bit smaller so we can get everything connected. I will say it is a little bit different with connecting if you are used to the downloaded version of the app. So you still have to turn on the pH probe. So now it's flashing red, it's broadcasting. I click on sensor data collection. And now I click on wireless. So this is what's a little different than the downloaded version or the native version of the application. Say wireless. And now I'm going to look. There's a barcode on the back here with a number. You can't really see. It's too tiny in my camera view, but it's back there, I promise. And you find it with the serial number and you say pair. And you wait for it to pair. And now it should flash green. and it's all paired. And you see it's connected, and you say done. How cool is that? I didn't have to bother IT. I didn't have to have administrative rights. Awesome. All right, and I have it on at the same time as spectral analysis. Super cool. All right, so I need to set it up for my data collection. Again, I'm just taking pH data of all my beakers here. So I don't need pH versus time. I want to do what we call selected events. So I just want it to, when I tell it to collect a sample reading, to just grab that data point. So that's selected events. So I'm going to go into mode. I'm going to change from time-based to event-based. And I'm going to go into selected events. I'm going to change the event name to sample number. And I'm going to say done. And I don't even need the graph right now. It's just going to take up space. But I do want to see a much bigger meter. So if you missed that, I did that kind of quickly. A lot of people don't know that you can change what you see in the graphical analysis screen. They don't know that you can make this little tiny, tiny, tiny meter much bigger, especially if you're doing class demos or if you have a group of students around a computer. It's really nice to go in and turn on this meter. So that is up here in this square of squares. Turn that on, enable that meter, and that is super helpful. So I'm going to make this, bring spectral analysis back up. I'm going to make GA really tiny because all I need really is the meter and to make sure that data is being collected. Okay. All right. Okay, so my spectrometer is all warmed up. I have my cuvette of water. This is just water, ready to go. All my solutions are water-based. So I just put a cuvette of water, put it in, and say finish calibration. All right, and I like to do a warm fuzzy, and this always scares a lot of people, but it actually solves a lot of problems down the line. I go ahead while water is in there, I press collect. Now, if you get a bunch of garbage looking stuff, that means you're good. That's what it's supposed to look like. If you see a really beautiful peak, that means something went really wrong in your calibration. So I always like to do that. It also teaches students about scales, because if you look at this y-axis, this is 0.005. That's basically 0. So I mean, there's a lot of good in doing that, but I know it scares people a lot. Okay, so I got my first sample already prepared. Put my first sample in my spectrometer. And again, this is this is full yellow sample, so my fully acidified version. Full in the 430 peak. And now I have a really pretty spectrum. It's stable. I'm going to go ahead and press stop. Okay, I want to do all 9 samples at the same time. We're gonna do spectrum and pH back to back all together. For the sake of time, I'm going to be a little bit lazy about my data collection here, and I'm just going to be using a wash beaker. You probably don't want your students doing it this way because it will create a little bit more contamination in your samples and it will lead to less accurate data. You want to be using a wash bottle and drying. But this is good for today's demo to save us time. And then I'm going to, the other thing that I'm kind of saving time with is I really do want to make sure my pH probe is secured when I take pH data. It's not good to be holding electronics when you are collecting data from it, but I careful to only hold the black part. I never want to hold the BNC portion or the amplifier portion. So I'm going to make sure that my pH reading is stable. Go ahead and press collect. And then whenever I press this keep button, that means the software is going to grab that pH value. So I'm going to press keep. All right, and this is the part where I just rinse and repeat. So now I move on to my second sample. So this one has a little bit of base in it. Press collect in spectral analysis. And get a nice spectrum. Press stop. Rinse. Grab my pH reading. And see why I want to look at that meter screen nice and big so I can see when that pH is pretty stable. Press keep. Done. All right, and here I go. How are the questions coming along there, Noose?
Some nice ones in here. Let's see. One just popped up. If you have a pH sensor mounted on a clamp and a ring stand, is there a problem with where the clamp is placed on the sensor? What do you think, Melissa?
So again, I try and put everything on that black part of the pH probe.
Mhm.
I never, ever want to clamp on the BNC.
And I've put it on the electrode amplifier part at the top, you know, from side to side. I haven't had any trouble.
Yeah, if you're not
down.
moving it, that's fine.
Yeah. Yeah.
The black part is the safest. The BNC is always a no-no.
We have a thing called an electrode support, and it's really nice. It's not very expensive, and it holds it, you know, in a nice position for experiments like this too. Yeah, put it on the amplifier. Just don't over clamp it, you know, because it is plastic, so you don't want to crimp it down too far. So, Melissa, the challenge today is to beat your data from yesterday. I don't know if you're going to be able to do it. Yesterday's data, I won't ruin it for everybody, but yesterday's data, she was within, what was it, 1 or 2% of the
Yeah.
published value of the Ka value, or the pKa value. And it was like my jaw dropped. It's like that was something. Another thing that we were talking about yesterday, you know, you could have students do pH while, you know, you're doing a demo with the Spectra. The other possibility is, you know, my classroom had a Peninsula lab station. So one group across the station could be doing the Spectra while the other is doing the pH. So there's multiple ways that you could set this up. I think it's really clever that Melissa came up with doing everything on one device, but that may or may not be practical or easy for you to set this up. You could be, yeah, yeah. I'd love to hear other ways to do it. You could be collecting pH on well, if you're using a Go Direct, you could be collecting pH on your phone, like Melissa said earlier, or on a Lab Quest. Can this be done with older sensors? Of course. You know, there's no reason you couldn't read the pH with a white plug, what we call the Lab Quest sensors. Those, by the way, a lot of people don't realize they will work with graphical analysis.
Yep.
Long as you have a Lab Quest or a Go interface, you could use
You could be
your
doing this exact same thing. There would just be a cable right here. It would be
would
the
look a
exact
kind
same thing.
yeah, yeah. Now, as the graph develops, we've had a couple questions, I think, on colorimeters. Notice where the peaks are, and Melissa will point them out when she gets all the data done. With our colorimeters, you have a limited number of wavelengths, and you only got 4. And so, what turns out to work well with BTB is that the peaks are very close to the wavelengths on the colorimeters. So you could do it. It's just on the colorimeter, you're not going to have nearly the pretty graph. Yeah. But it's not impossible, you know, that you could measure the absorbances at one wavelength and measure the absorbances at another wavelength. And so it could be done. But you know, the SpectroVis does such a beautiful job. The other thing that's just think about the equilibrium, right? Shifting it from the left to the right. Melissa is now shifting it to the right. Okay, and look what's happening to the spectra, you know, as she shifts it to the right. Okay, and I think when she came up with this, I thought that was brilliant. Have you done this experiment with other indicators? No. um, there, and we'll challenge you to do that. Phenol red was one we talked about because I think it's in our AP book, or it's in the College Board AP book or something. But that's one of those ones that doesn't have the nice color change. This one, once again, it's all credit to Melissa. She, you know, BTB has this neat way of meeting up with the equation, you know, and you know later, of course, you'll see in a minute how to get the Ka. How are you deciding when to press keep? What she's doing is she's watching the meter. Question was, how do you decide when to press keep? She puts it in the solution, watches the meter until it stops changing, or at least what we call stabilizes, and then clicks keep. Sometimes it will stop, and sometimes it just will kind of bounce a little bit. And so we say stabilize. So watch that value right now, 9.94, 9.95. You know, you kind of pick a point and you just hit keep and it grabs the data. So I think you're there.
I'm all done.
I soft shoot around it. I'll shut up and let you finish the presentation.
All right, we got all our data. Okay, so now we got to do some analysis. All right, so let's pull back up our worksheet. So on the second tab, we have a data analysis. So
Melissa,
however
can
much,
you zoom that up a little bit?
oh yes, yes.
Thanks.
So however much work you want your students to do in terms of math, again, it's all written out in the Google folder. But you could just put all your numbers in here and it will spit it out for you. The first step is to bring graphical analysis out here and spectral analysis out. And we want, and I don't need the table, I want to get the absorbance peaks at 434 and 620 nanometers. And I want to write them in graphical analysis. So luckily, all the values will be in order. So it's actually pretty easy to transfer. I could spend all day looking for, what am I looking for again? 435. I could spend all day here looking for 435 and I will never find it. Every spectrometer is different. Find the closest one and stick with it. Okay, mine is 435.2. My partners or the lab bench next to me might be 435.7, and they need to stick with that. The next lab bench might be 434.9, and they need to stick with that. That's just how it is. All right, so in graphical analysis, I'm going to add a manual column, and this is going to be absorbance at 435. And I'm going to say apply. I'm going to get rid of the meters. I don't need those anymore. And sample number 1 was my most acidic, so it had the highest absorbance at 435. So I'm going to type in all my values from here. So for those of you who might have missed what I just did, maybe you don't know that you can add your own data to graphical analysis, but you can. It's called adding a manual column. You can also add calculated columns. We're going to do it again because we need to show it at, we need to pick the 620 peak. All right, I'm going to go over and I'm going to pick 620. And so I'm going to click on the little dot, dot, dot column. If I mouse over it, it says column options, but we just call it the dot, dot, dot. I'm going to say add manual column. And then I'm going to rename it. Oh, sorry, not 600, 620 nanometers. Apply. And this is the one that grew in. So sample number 1 is going to have the lowest absorbance value. And all I'm doing is typing in the number from sample 1 to sample 9. And yes, you could do all of this in Google Sheets if you wanted, or Excel, depending on your goals as a teacher. But I personally like graphing in graphical analysis, and I like calculating in Google Sheets or in Excel. So we're going to do a little bit of both. Okay, so I've gotten all my data from my spectrum. And now I'm going to take my pH and my absorbance data. I'm going to select it. Oh, first, what I would show you right now, I can show you if you do this with a colorimeter, this is the data you would be getting. Because you would have absorbance at 435 around there. What are the
430 and 470.
Yeah. Oh, well, what's the
635.
635. So it'd be close. But your students would get data like this. So they'd still see the absorbance at 435 went down and the absorbance at 620 went up. So obviously they wouldn't get the full spectrum, but they would see one species went away and one species came in. So just as, because we had so many colorimeter questions, I thought I would show that while we were there. Okay, so back to the analysis portion. We're going to select the pH absorbance. I'm going to control copy. So I'm copying. I'm on a Windows, so I'm copying that data, and I'm going to go over to my Google Sheet, and I'm going to paste that data in this box here. And all my calculations happened. So we have some time. I'm going to explain what these calculations are doing. So the main calculation that's important is the fact that we had to do a corrected absorbance, particularly at 435. So if you look at the spectra, 435 never goes to 0. And that's because this is not, let's pull up the structure again. There are more pKa's on this. There are more acids to lose. So there are more species that would absorb in the UV that we do not see. And part of them absorb, they have a shoulder that are obscuring our 430 peak. So this will never go to 0. So we need to make sure we subtract off this value, because otherwise it will mess up all of our data. So all we're doing is just bringing this value down to 0 to make sure that we've baselined it. So that's what this correction is for. We are just taking this 0.396 and subtracting 0.099. 620 doesn't matter as much because it does go to 0, but we did it for 435, we'll do it for 620. So we're going to say 0.743 minus 0.003. So we get a 0 here and a 0 here, which is why there's null for sample 1 and sample 9. So remember back when we were talking about Henderson-Hasselbalch, the number we care about is pH versus this natural log. So let's pull up graphical analysis. We're going to do one more manual column, and we're going to do the natural log of the base over the acid. Doo-doo-doo. All right, and I'm gonna copy this. And I'm gonna paste it. And now, and for those of you who don't know how to manipulate what's on the graph of graphical analysis, you click on the thing you want to change. I want to change what's being shown on the x-axis. So I click on the x-axis. I want it to be the natural log. And on the y-axis, I want it to be the pH. And I'm going to, let's see, double click. Now I'm going to select my data and do a zoom in.
Time for a drum roll.
And now I'm going to do my linear fit, right? And my y-intercept, so my B value should be the pKa. The literature pKa value for bromothymol blue is 7.1. So my B value should be close to 7.1, and it is 6.983.
Ah.
It was a little bit better yesterday.
Yeah, yesterday was 7.0.
Yeah.
Yeah.
But again,
Still.
I made these in graduated cylinders, in beakers, and
Yeah.
I also made them on Saturday, y'all. So these are some pretty stable solutions, and they're pretty robust. So it'll probably work with your high school students. I always like to make it as if I'm a high school student, because then I know it'll really work when it's really high school students.
Yeah.
But that's how you get that pKa. And then if you want to continue on to getting your Ka, you take 10 to the 6.98. You can compare across the class. You could do statistical analysis. You can do all kinds of stuff. So that is how we do it completely graphically. No ice table required. Let's see. Yep. So again, just to kind of summarize, we looked at, yeah, any questions? I feel like we kind of did a good summary there at the end. I don't need to, let's jump into questions. I'm sure there's questions about it.
So there were two questions. Why are we doing why did you do natural log or did you do base 10 log?
I did natural log in the Google Sheet.
Yeah, okay. Why that instead of base 10 log? I don't remember. I can't think of a reason why.
I didn't have a reason.
I did.
It was quicker to type natural log.
Yeah. Well, I was
than
just
base
thinking,
10 log.
the pH typically is, yeah, anyway.
I should probably do base 10 log. It's more like students, it's easier to explain to students.
Yeah.
I should have probably done base 10, and all my equations were in base 10, so I should probably go back and change the worksheet to base 10. Yeah.
I thought you might have a trick that I didn't know about. So
No.
yeah.
No.
Well, the other question that just came up was the correction value. That, and I think if I heard you right, that had to do with contaminants or other species in solution that were absorbing at that wavelength and trying to account for them in some way. Is that why you did the correction value?
Yeah. So, and explaining it to students, I do think could get confusing. You can just say there are other things in this solution that absorb that we can't see.
Yeah.
And we have to, and they are absorbing at this wavelength, and we need to subtract that out. That's probably the quickest and easiest way to do it. If you want to get a little bit more into talking about this acid has multiple pKa's, because we know bromothymol blue has multiple pKa's, you could talk about the other pKa, and you could talk about,
isn't it? I think it's
yeah,
diprotic.
there's another one down at 4, and you could talk about that one.
Yeah.
You could even maybe go down to it and see it turn clear and be like, this is the other species. Like, it kind of just depends on how you want to get into it. But if you just want to keep this kind of isolated, and the quickest way is just, there's another version of bromothymol blue in this solution that we cannot see with our eye, that we have to subtract off.
Yeah. And that kind of relates to another question that came up. How did you select the wavelength when doing the data selection? How did you decide which wavelength to pick? Was it just the lambda max or was there some other reason?
That is an excellent question because you can pick a variety of wavelengths in this. In fact, if you look in the literature, a lot of different wavelengths are used, and you could pick a wavelength that is closer to 460, and you wouldn't have to do as much of a subtraction. And maybe you could even analyze the data, and maybe you wouldn't need to do a subtraction at all. But I just picked the ones that literature did the most often in kind of my cursory glance. But really anywhere between 430 and 460 is commonly picked here. It's a pretty flat peak, so you could really pick anywhere in here. The peak, I mean, 620 isn't even the peak here, so it really doesn't matter as long as you're at a point that has a good absorbance. You don't want to pick anywhere in the middle where
Right,
both
right.
species are, but that's why you could do it with the colorimeter, because the peaks are far enough apart.
Yeah.
But yeah, challenge your students. This would be a great inquiry experiment, especially if you're having them kind of get more into spectroscopy. And do you always have to pick the peak? I don't know. What do you still, does Beer's
Mhm.
law still hold if you pick a shoulder? You know, it's kind of,
Yeah. Yeah. I
yeah.
love the way the transition in the equilibrium is so easy to demonstrate
Yes.
as you're shifting from the acidic form to the
I mean,
basic form.
look at this beautiful rainbow. Like you can't, like students, like so many students, like a light bulb just goes on when they see that. It's so much better than, you know, that pink that what just happened,
Yeah.
you know?
Yeah. Well, my students would want to take their phones out and take a picture.
Yeah, yeah,
And I would say, okay, class
yeah.
set of colorimeters, only one older ocean optic spectrometer. When you do this with the colorimeter, do you just take the absorbance of both wavelengths by punching the buttons while the solution is in it? Not recommended. Uh,
I would do one wavelength, set it to one wavelength, do all your solutions, set it to the other wavelength, do all your solutions.
and check the calibration, right? So at
Right.
each one of those, make sure that the blank, the water is reading zero. If not, you would once you've switched to a wavelength, make sure you push the cal button. So you could do it that way. By the way, the ocean optic spectrometer won't work with spectral analysis, but it will work with Logger Pro. So if you've been doing it that way, then you know that you could still do that. But spectral analysis will disappoint you, I guess, in a sense. But ocean optics doesn't exist anymore, so just it's one of those things. So we've kind of moved ahead. But yeah, if it's still working, fantastic. Just use it with however you were doing it. So so does the buffer system matter besides? So when I asked this question to Melissa, I said, why are you using phosphate? You know, why not just use sodium hydroxide? What was your answer, Melissa?
It will be very tricky. And especially if you're having your students prepare this, you will not get good results. Um, so, and again, this is a poor man's buffer. So it looks a lot more complicated than it is. You're really just making a 0.1 molar salt solution here and a 0.1 molar salt solution here and adding it. You just want one solution that's super acidic and one solution that's super basic. Especially because you're around, the pH is 7.1. So everything, if you are making all these solutions in water and you're working in an environment that is rich in carbon dioxide, everything is going to affect that solution. So if you're trying to titrate it with strong acids and strong bases, it will be very difficult to have these solutions sitting out here and not have them constantly be changing pH. So you do need some stability with a buffered solution. But again, it is not a complex buffered solution. It is not making real buffers. It is just using salts, salt
Just
phosphate solutions.
salts of the monoprotic and diprotic phosphate, right?
Yeah, yeah,
Yeah, and BTB, everybody has BTB. That was kind of what made my bulb go on when you first showed this to me, was like all those chemicals I had in the stock room at school. And so none of these are weird dramatic chemicals. And the fact that you can do this whole experiment with whatever Vernier equipment, as long as you have some way to measure color spectra, and you could do this experiment with probably what you've already got in your school.
yeah.
So yeah.
And you do want to get fairly close to you're only getting so much data, so you do want to get a little bit closer than ±1 pH unit. But you just want your students to have a good experience. So I think using the phosphates, salts is very helpful for that.
Well, it's so easy with the Henderson-Hasselbalch equation to just do a half titration and call it a day, right? And so here's one where, that log factor actually is a factor that you take account of and you pay attention to, without just saying, well, I'll titrate the thing and then I'll just go at half the volume of the equivalence point, and whatever the pH is, that's equal to the pKa. But which is certainly fine. I mean, we've all done that. But now we're not just minimizing the importance of that ratio of the base to the acid. I think that's super cool that here's an experiment that looks at that part too. So,
Yeah.
any other questions, concerns? I'm seeing a lot of stuff pop up in chat. Thank you
Yeah,
very
great
much.
questions.
Yeah. What do you think? Let's do a little quick poll on this. Would you use this experiment when you're teaching equilibrium? What do you think? All right.
Oh, yeah.
Jennifer, yeah.
All right, good.
That's great to hear. Yeah. Yeah.
Awesome,
Yeah.
awesome.
Look at
In 2
oh, 2
weeks.
weeks.
Love it.
Go
Perfect
for it, Natalie.
timing.
Yeah, yeah. I'm so glad. We need to hear more about this too. If you guys have other experiments that you want to do that involve, our technology, please let us know, because we're constantly looking to support our customers, and we're both chemistry teachers here, and we know the struggles that some people have. And so if we can help you, particularly with this one, this one caught my eye the most because I had everything in. I told Melissa yesterday, I said, I wish I'd known about this 10 years ago when I was in the classroom. I would have done this one in a heartbeat, because it's just so cool.
Yeah. So we got some NGSS standards here for the experiment. So take a look at those if your school subscribes to NGSS. That links out to the full thing. I just have some bullet points there for you. And then if you need some other ideas for Le Chatelier's principle, we do have some actual Vernier written up experiments in our AP Chem book, which uses the phenol red. And Advanced Chemistry with Vernier and Chemistry with Vernier both use that iron thiocyanate. But again, we're trying to get away from the more expensive and less environmentally friendly chemicals. So that's kind of why we wanted to look at bromothymol blue a little bit. If you don't want to use a spectrometer, don't want to use pH, don't want to look at the concentration aspect of Le Chatelier's principle, you can also look at temperature, right? Copper or cobalt are very popular. There's a great Royal Society article in here that looks at this equilibrium reaction. You can use any temperature probe, but Vernier makes temperature probes. So that's a great one to do. There's also a JChem Ed article here if you want to look at pressure fluctuations with carbon dioxide. There's a great JChem Ed article that just came out. And I think I even put this article in our Google folder for you. So if you have a pressure sensor, take it out, look at that one. Another great way to do Le Chatelier's principle. All right, and then that was the kind of the last bit of things I wanted to say. So yeah, any more questions? Definitely throw them into chat. Dylan will put that survey up again. Again, shout out to those responses in the surveys. We do listen to them. This was the most requested topic last year, so we listen. Whatever you want, if you want experiments, if you want webinars, we want to know what you want so we can get it for you.
We plan to do this for an online lab
Interesting.
class. What do you suggest?
Interesting. It would probably
You
make
could
a pretty decent online lab class.
you could GA Pro the data.
Are you like sending chemicals out, or is it more of a virtual environment?
Yeah. Because if it was virtual, you could GA Pro the data, but you would still have to probably collect the spectrum and then share it somehow so that students could
Oh,
access
yeah.
it.
We don't sell kits or chemicals, but this would be really good because, I mean, bromothymol blue isn't that toxic. Like I said, they're pretty stable this way, so you could make them up. I don't
Yeah.
know about sending the extremes, the acid and base, but all of those are around pH 7, so you could probably send them. I don't know. They pick them up somewhere. It's a
Yeah.
lab quest with a pH probe.
Would work great.
Interesting. Yeah. I think you could do it.
Yeah.
It would make a good virtual lab for sure. But
Right.
yeah, setting up a lab kit would be difficult. We don't sell chemicals or anything like that. But definitely setting up these yeah, because they're all around pH 7. So you could make them and have the students pick them up. They're pretty stable. So some company mails it at the beginning of the semester. Yeah, the bromothymol blue indicator is sold by Flynn, but then you have to make the solutions. So
That's all in the spreadsheet, so
yeah,
relatively
and
simple.
students could do it. I mean, if they have other chemicals, but yeah, yep, lots of COVID money
Good way
still.
to use that COVID money. Yeah.
Still, yeah.
Sounds good. Dylan, did we forget anything?
I think we're good. I just saw someone with their hand raised, so I wanted to make sure that we got to their question. But aside from that, I think we've hit everything. Does anyone in the chat feel like you didn't get your question answered? We'd love to hear from you.
Yay, thanks everyone for coming. Shouldn't we use the buffer? Again, it's not in a buffer, it's in water and salts. So no, it's water is the solution. It's not in a buffer.
All right. Well,
All
thanks for
right.
coming, folks.
Absolutely. We've had a blast. Thank you all so much, and we will get this recording to you soon. So have a good one.
Yeah.